In this unit, we're looking at the integration of metabolism. So essentially what we're doing is pulling together a lot of the content that we've covered in the last few weeks, particularly on carbohydrates, protein, and lipid metabolism, and looking how all of that kind of comes together in the body. Obviously, when we eat or when our body's functioning, there's not only one energy source, so we've kind of looked at them individually, but then we want to think about how all of that works together. Another thing that comes into play here is how the body reacts to different states or conditions. So how the body reacts and uses different energy sources in a fed state versus a fasting state, or for example, during high intensity exercise versus low intensity exercise, during an illness or injury, those types of things. So this week, really, hopefully you'll be able to take, sort of have a refresh on the content from the last few weeks and put it all together sort of in the big picture of how that, how the metabolism of those different macronutrients integrates. And then later, as we move forward in the course, we'll look somewhat at vitamins and minerals, how they also play into metabolism, to some of those metabolic processes, but we'll focus for now still on the macronutrients and integration of those in metabolism. This figure has a lot going on in it, but I really like it because it pulls together all of these different aspects of protein, carbohydrate, and fat metabolism. So I want to break down a few things that are going on in this figure and kind of talk about those a little bit. One is that the issue of the just kind of how things are written in these types of metabolic pathways, and this is something you know, but just as a reminder, those whenever there's a two-way arrow, and I'm just picking one here, but any of these two-way arrows or two one-way arrows essentially tell you that the reaction can go both ways. So that's a big deal in metabolism because it tells you whether that compound can be converted back and forth between another one, or whether it can only go one direction. So when there's a single arrow, one arrowhead, then that means it can only go one direction. And that's really important because that means that indicates to you that's going to be a regulatory step. So if one compound can only go one direction and it goes that direction, then it's really committed to going down that metabolic pathway. It can't sort of change its mind, so to speak, or switch what it's doing to go the other way. So this here is a really classic example of a important one-way reaction in metabolism. So this conversion of pyruvate to acetyl-CoA, and this image shows it a little bit different than some do. It kind of shows it going separate to acetyl-CoA, but really then that acetyl-CoA isn't totally obvious that this is feeding down into the TCA cycle, but just to be clear, that's what's happening there. So the pyruvate also forms some of that oxaloacetate that's needed to sort of, sometimes we say prime the pump for the TCA cycle, so we need a little bit of that to get that TCA cycle going. But this key step is this pyruvate converting to acetyl-CoA. Because that is a one-way reaction, once that happens, we're really committed either to storing fat, so making fat, or to going into the TCA cycle for energy production. And remember the TCA cycle, then following that, we will often go into the electron transport chain, which then produces even more ATP. That's really where the majority of the ATP or energy is produced. So this is really a key metabolic step, and it's really important to recognize that that's a one-way step. Again, once the acetyl-CoA is formed, that can produce energy, or it can go and store things as fat. But what it cannot do is go back up the pathway to produce more glucose or glycogen. One other thing that pyruvate can do is it can make lactate or lactic acid, and that is a two-way reaction. It can go back and forth between that. So if our body is short on other substrates, so short on carbohydrates or glucose, for example, then we can utilize lactate for an energy source. So that an example of that is in heavy exercise, perhaps in an anaerobic condition, that sort of thing, where we can't, where we're out of glucose and we can't get the glucose going in there fast enough, the lactate might be an option for that. So that is, those are a couple options for pyruvate. So pyruvate is really a key step in metabolism. So kind of essentially anything that from pyruvate that sort of goes, what I, on this image looks like down the pathway, down the metabolic pathway, that's producing energy. So that's when our body has a need for ATP and energy. Whereas if we go back up this pathway, if you want to think about it that way, That's when we don't have a need for energy, so our body has met its energy needs, and then we could store that as fatty acids. So you can kind of see from that too, this is where the whole concept of any macronutrient, whether it's protein, carbohydrate, or fat, if we have more than our body needs, we can store it as fat. Because if we take in too much carbohydrate and it starts in through this pathway, sorry, this is getting really messy here, to pyruvate, then it can go back up and be stored as fat if we don't need it. The same with protein. So those amino acids, so we have lots of different amino acids, and they come in the metabolic pathway at different places. So you kind of see them all over the place in this image, but essentially they all kind of filter into somewhere that then they could either provide us energy or provide us fat for storage. Many amino acids can be converted to glucose. So those are give us the possibility that if we don't have enough carbohydrates and our body has that glucose need, that we can convert them to glucose. If they can't be converted to glucose, then those are ketogenic amino acids. But most amino acids can be converted to glucose as an option if the body has that glucose need, or it can be used for energy. Now, in reality, protein is not our body's preferred energy source because it's considered really a quote unquote expensive source of energy, because there are so many other functions that proteins can do that carbohydrates and fat can't do. We've talked about that already. So it's really not the body's preferred source of energy, but it can be used for energy. And if we eat too much protein, it can be too much protein, more calories than our body needs from protein, that can be converted to fat. I guess if I said that correctly, so that our total caloric needs is beyond what our body needs. Even if that comes from protein, that will be converted to fat.